About sp hybridization. I have already made videos on sp2 and sp3, so basics are covered in that. You can watch those videos. Okay, so what we are going to study here is an example of sp hybridization with respect to carbon. Now, as I told you in my previous videos also, sp3 is for carbon-carbon single bond, sp2 is for carbon-carbon double bond, and sp is for carbon-carbon triple bond. So, any triple bond, not necessarily carbon-carbon, it could be carbon-nitrogen triple bond, that's cyanides, right? Or nitrogen-nitrogen. So, that's sp hybridization. So, to begin with, let's take an example of the simplest alkyne, acetylene. Okay, so the central atom over here is carbon. So let's start. I have already mentioned what points you have to follow. So atomic number of central atom is carbon, that is 6. So write its electronic configuration. Always start with atomic number, electronic configuration, then go for the ground state configuration. Now 1s2 does not take part in hybridization because of the large difference in the energies. So s and p are going to mix with each other because of small difference. So in excited state, what happens is electron from the 2s goes to the 2p. So 1s will remain as it is. Electron from 2s will go to 2p. Okay, this is your excited state. The next step is sp hybridization. Now, what is sp hybridization? One s orbital plus one p orbital combined to give two sp hybridized orbitals. So this is the definition, right? Okay, so one s and one p. So these two will hybridize. So what are we going to get? We are going to get two sp hybrid orbitals. These are your sp hybrid orbitals, two sp hybrid orbitals. Now these two are left, right? So these two are your unhybridized orbital. Unhybridized orbital. Which are these orbitals? P orbitals. Okay. So you can, now you know that P, this is Px, Py, Pz. So let's say that Px has gone there. So now what is left? Py and Pz are left, unhybridized. Each one is having what? One unpaired electron. Now let's say this is for carbon number 1. The similar will be for carbon number 2 also. Okay. So I'll draw carbon number 2. Right. Now, look at this molecule. What you see here is there are 3 bonds between the 2 carbons and a single bond between hydrogen. So, always remember, hybrid orbitals, they form sigma bond, okay, and unhybridized orbital form pi bond. Okay, if you look at this, this is sigma, sigma, and one of the bond is sigma, and the remaining 2 bonds are pi bonds. So what is sigma? So there is one carbon-carbon sigma bond. So this is your carbon-carbon sigma bond. Then there are 2 carbon hydrogen bonds. So here this one will form a bond with hydrogen. This one will form bond with hydrogen. Now there are 2 pi bonds. Pi bonds are formed between what? Unhybridized orbitals. So as you can see over here, these are the 2 unhybridized orbitals which will form pi bonds, right? Now I told you how to write the hybridized orbital, one large lobe and one small lobe. This is the notation for hybrid orbital, and unhybridized orbital will be what? Both the lobes are same. So we'll draw the carbon now. So 2 carbons are there, right? So let's draw the 2 carbons. So there are 2 hybrid orbitals. So we will draw these 2 hybrid orbitals in a linear fashion. Okay, 2 hybrid orbitals. Now there are 2 unhybridized orbitals. Unhybridized orbital will be of same shape. So this is one and this is the other. Okay, these are the 2 unhybridized orbitals. Similarly, draw for the second carbon. Now you can see the carbon-carbon overlap. There is a carbon-carbon overlap, yes or no? So that is between the hybrid orbitals. So these are the 2 hybrid orbitals showing the overlap. This is your carbon-carbon overlap, show the pair of electron. And this is your unhybridized orbital, show the same sized loop. Okay. Now you can see this, the one, each carbon is forming a bond with hydrogen. What is the shape of H? Spherical. Each one shares electrons, so a pair of electrons. So this is your H, right? So this is your sp2 s bond. Yes or no? So this is also sorry, not sp2, sp s bond. Sp s bond. Right? Now, what you have to show is the overlapping. So these are the pi bond, which are formed by lateral overlap. So this bond will overlap with each other, this orbital will overlap with each other. So these are the two pi bonds. So above the plane and below the plane. Getting it? These are your pi bonds. So how will you name these pi bonds now? So I'll write it over here. This is sigma bond, sp overlap. Then that's one. Then there are two carbon hydrogen sigma bond, sp overlap. And there are two carbon carbon double bond, two pi bonds, not double bond, two pi bonds. And what is the overlap? pp overlap. Are you getting this? So this is your this is your pp overlap. Okay, this is your pp overlap. This is this sigma bond is your sp overlap. And if you look at this molecule, all the the sharing is taking place over here in a linear fashion. So what is the geometry now for sp hybridization? Now you should remember this. The geometry is linear. Okay, and the bond angle for sp hybridization is 180 degrees. Okay, so linear geometry 180. So be it any hybridization, sp hybridization, it is always 180 and the geometry is linear. So whatever I have explained you, I have just noted down or in point wise over here, so you can take it as notes and see this is the overlap that is taking place. And you can see this cylindrical cylinder over here represents the overlapping of the p orbitals above and below the plane. So it looks like a cylindrical electron density around the single bond, okay, along the axis. So this is the linear overlapping. You can see this s overlap and this is the p over sp overlap, and this is the overlapping above the plane and below the plane, which looks like a cylinder. So this is your ethyl, okay, acetylene. Fine. Similarly, we can show the hybridization for carbon nitrogen. So which type of compounds will give you this type of hybridization? Anything having a triple bond. So apart from C triple bond C, which one has a triple bond? C triple bond N triple bond N. So all of them are going to show the sp hybridization. Now carbon, so we have done. So let's write for nitrogen. Okay, so everything remains the same. One is 2, 2p3. So all the points are same. This is, now I won't draw 1s. Okay, then this is your ground state. In excited state, what happens? S electron goes to p. So here the pairing of electron will take place over here, right? Now this is your excited state. Now let's say sp hybridization. So it will take place for the lone pairs first rule. So you can write the lone pair over here and this. So you can now see that the lone pair of electron is in the hybrid orbital. So your lone pair is in hybridized orbital. Okay. So two sp hybridized orbitals are formed and these two are unhybridized orbital, which will give pi bond, and the single electron over here will give sigma bond, and lone pair of the electron doesn't take part in bonding. Remember this. It doesn't take part in bonding. So while drawing also we will draw exactly the same way we have drawn for carbon. So let's draw for carbon over here. Now let's take example of HCN. Okay, HCN. Now you know the structure, so let's keep this structure in mind and draw. Now this is carbon. So there are two hybridized orbital of carbon, right? And these are the two unhybridized orbital of carbon. Okay. These are the two unhybridized orbital. Now there is a carbon nitrogen carbon nitrogen sigma bond. No, so you show the overlap properly. So show the overlapping first and then the lateral overlap. This is your along the axis giving you the sigma bond. Now this is the nitrogen. So nitrogen is also having two sp hybridized orbital, right? And there are two unhybridized orbital. So they will be like this, right? Along the x-axis show hybrid orbitals, along the y and z axis show unhybridized orbitals. This is for nitrogen. Okay, now nitrogen is having a lone pair of electron. Where is it present? In the unhybridized orbital. So this is your lone pair of electron. Okay, and each unhybridized orbital is having a lone pair of electrons. So I'll show opposite spin so that you can understand the overlapping. So this one overlaps here, this one overlaps over here, and this is the carbon hydrogen overlap. This is your hydrogen, and so you can show a pair of electron over here. So this is your sigma bond, this is your sigma bond, this is lone pair which is not taking part in bonding, this is the pi bond, and this is also pi bond. And since it is sp hybridization, geometry is linear. Okay, so always remember, two sp hybrid orbitals are formed. One sp hybridized orbital contains unpaired electron which forms a single bond. One sp hybridized orbital contains lone pair which doesn't take part in bonding, and two unhybridized orbitals, they give you what? Pi bond. So what types of overlaps are there? Carbon nitrogen sigma bond which is having a sp-sp overlap, carbon hydrogen sigma bond which is having a sp-s overlap, S stands for hydrogen, and carbon nitrogen pi bonds which are two, this is one which are two, which are having pp overlap. Okay, so this was all about sp hybridization. Oxygen is not having a triple bond, no, it's having double bonds, so it will show sp2. So we haven't included oxygen over here, right? And I have summarized all the three hybridizations over here. So look at this. So this is your sp3 hybridization, saturated systems. sp2 and sp are unsaturated, and sp2 you have double bond, sp you have triple bond. Geometry is tetrahedral for sp3, sp2 is planar, and sp is linear. For if there is a lone pair of electron in sp3 hybridization, like nitrogen has one lone pair of electron, so bond angle reduces because of repulsion between lone pair and bond pair. So repulsion some more. Here there is repulsion. Here, sorry, here this is bond pair, no? Bond pair repulsion, because there are no lone pair. All four are single bonds, so bonds are there. And in water there are two lone pairs of electrons, right? There are two lone pairs of electrons. Sorry about that. Just a second. Okay. There are two. Sorry, two lone pairs of electrons. Okay, so the band, now see the shapes also I've mentioned over here. You can go and watch that sp3 hybridization. I've explained everything in that. And because of these extra repulsion, increased repulsion, the bonds, they come closer to each other and the geometry changes. And these are the examples you can see over here. Alkane saturated system will give you sp3, alkenes, aldehydes, ketones, which are C double bond 2 gives sp2, sp is given by alkynes, nitrides. And this is an important point over here. Hybrid orbitals form sigma bonds, unhybridized orbital forms pi bonds. If there is lone pair present, lone pair is also present in the hybrid orbitals. Okay, and remember this, the shape. A normal p is this, s is this, hybridized is one large lobe and one small lobe. So these are some of the key points that you can remember. Thank you.